So hello, if anybody's still on the break, come on in. Otherwise you'll miss the critical opening slides and you'll be scratching your head through the rest of the presentation. But anyway, we get started. So Throughputer is a development stage platform as service for high performance, particular real-time type of cloud applications. So the processors have not getting much any faster for the past 10 years, while the applications performance demands keep increasing in particular the real-time type of interactive applications that need to deal with real-time events of all types. These type of demands keep on increasing, so we need to find increasing levels of concurrency within the applications to provide the speed up where the hardware is no longer providing the automatic speed up. And we are running this type of applications. We could call them microservices that are made of multiple sub-services in on a dynamically shared cloud resources. This creates a challenge in terms of overhead. We cannot really afford to statically assign to any given application or its instance or its task group all the resources that it would potentially need to satisfy its peak demand level of processing load. The peak demands would be somewhere in the order of 1,000 times the typical processing load, so that would not be, we would not get the cost efficiency benefits that we do need from cloud computing. So we need dynamic resource management. However, that's far from trivial, in particular as we are the common type of architecture for creating modern web and enterprise application is made of these microservices, which process very single area of concern, short-lived individual transactions, which would normally just take a message, do something with it, and then exit. And these messages, they arrive somewhere in the neighborhood of microsecond granularity. This would mean that if you run this math, and this of course will be published on the website so you can check these numbers and come to your own conclusion, but essentially there's a paradox here. We do need to perform dynamic resource management at the scale of say microsecond at this processing load variations fluctuate, but handling all these computations and resource reconfigurations would demand more capacity than there are in a given pool of resources being supposedly optimized. So we can't proceed with the conventional approach of adding more middleware layers to deal with this optimization, the need for optimization. So what we see on this slide is we're intentionally simplistic model for estimating the cross applications on-time throughput performance if it did do the dynamic resource management using conventional software middleware. So here the critical, the blue line, is the product between the available throughput for the application, the green line, times the number of processing units. The product between the number of processing units in the pool of resources and the fraction of that resource available to process the client applications, that product begins to actually decrease as we try to scale up this system. So obviously this is not a long-term scalable approach. Instead, what we have to do is to take the overhead away from the software domain and do this real-time resource management functions in the fabric of the many core cloud processors. And that does achieve the real-time optimal resource assignment and handles all the associated reconfigurations and so forth without stealing any of the execution unit bandwidth from the client application, and thereby we get close to linear increase in the on-time throughput performance as we scale up these systems. So the platform as service, which is in development stage, at high level, there will be a parallel program development environment that essentially represents the user applications as independently schedulable and placeable component tasks in a fairly static manner. And then there is straightforward exchange between the development environment or the concurrent representation of the user applications and the dynamically allocated execution environment, which is made of many core processors that have a hardware operating system that performs all the runtime critical, performance critical dynamic resource management functions on behalf of the software. So how this would operate if you had, say, a block of 16 cores, and those would be shared by 4 application streams, and the application would have then a dynamic number of, say, instances, requests, so forth. And the hardware detects which of the application instances is ready to execute, had all the inputs available to it, and it can be scheduled for a processing resource to run, say, for a core allocation period of 1 microsecond, for instance. And it also honors the contractual entitlements of the application, so there's fairness. We essentially match the demand peaks. For instance, what is happening here is for the blue application, there's a demand peak. We match the demand peak of that application so long as we honor the contractual resource entitlements for also the other 3 applications, in this case, to the degree that those entitlements are actually met by the real materialized demand. So we don't statically keep these cores allocated to any application, even if they're entitled for a certain portion of the resources. We ensure that any application does get at least its entitled amount of resources whenever it has materialized demand for at least that amount of resources. But for the most time, the typical demand is much less than the peak demand. Most of the time, the applications don't have workload even for their typical or the entitled amount of demand, and without hurting the actual on-time throughput performance of that application, the resources that the given application, for instance, we could think of, for instance, the yellow application might have entitlement for, say, 1/4 of these resources, but if it doesn't have a materialized demand, those resources will be allocated to another application that can at that time actually utilize them. So there is no performance degradation for any of the applications due to this dynamic resource allocation. In fact, the opposite is true. Even the yellow application, when it does have a peak in its demand for the same reason, can get its peak met by getting the resources that would otherwise be idling in the quotas of the other 3 applications. And the resource assignments also are intelligently by hardware. Any of the tasks, for instance, do I have the pointer here? This particular, this particular task, if it keeps on running throughout these 4 core allocation periods, it doesn't observe any type of switching overhead. It is kept on a static core, and it's only the entering and exiting tasks that observe a minimum amount of switching overhead, but that's also hardware automated, so it's not really noticeable. It's just a few clock cycles essentially that there's a switch over. And regarding communication, this is actually an important technical problem. Assume that somebody needs to talk to this yellow application task instance here, but while the communication to that instance is happening, that particular instance may have been actually moved to this core. This is all automatically taken care of by the hardware, so the software can maintain a clean static abstraction of this actually highly dynamically allocated hardware. The way this is done is that the hardware operating system monitors the materialized demands for the different application streams and honors their contractual entitlements, and then for say for instance every 1 microsecond interval performs an optimal allocation of the resources among the applications, and also monitors the highest priority tasks or instances of any given application, maps them to their assigned resources, and performs the appropriate multiplexing reconfigurations silently on behalf of the software. And this is actually not much logic. So there's much less logic in this module than there would be a single processor core. Much less. We get further scalability by providing, which was illustrated in the previous slide, this type of many core arrays with their integrated hardware operating systems. We assemble multi-stage arrays of these, and then from these we provide also hardware load balanced clusters for massive request level parallelism between applications. And as was pointed out in the previous presentation, hardware does have the benefit that it must be designed for any type of say inter-task communication topology of the application. It doesn't make any assumptions of is this like a scatter-gather pipelining or any combination of those. And in this particular case, this is just a multiplexer which will automatically adjust without any software reconfiguration to the say inter-task communication pattern, which can be dynamic also for any of the applications that share this multi-stage many core architecture. So we don't actually need to make any assumptions or predictions of what type of concurrency topologies the mix of applications will have. They can be dynamic, and the hardware will serve them all, even if they change on the fly or one type of topology becomes dominant for some period of time. So this is kind of the direct benefit of having dedicated hardware resources, that there's no need for any type of software reconfiguration, no matter what type of dynamic or kind of collective load variations and demands the applications present, for instance, in terms of their inter-task communications topologies. So looking at the kind of the actual benefits of doing true real-time dynamic resource allocation versus having just a fairly static allocation of the capacity. Again, as in just 4 application streams, and we could predict the average over longer time periods. We would know with reasonable accuracy the resource demands of the individual applications, And assume that over time, and this is just 10 microseconds, but in this case, these real-time load variations across the 4 applications for each of the applications do average to their assigned quotas. However, at any, say for instance, this 6 microsecond window, looking at it, and it's a representative, we notice that the real-time load variations depicted by the green bars have hardly anything to do with the average demand profiles depicted by the black bars. So if we did have a static allocation, we would most of the time have, at the same time, we would have a block demand as well as statically reserved, but most of the time idling capacity in the same cluster. So obviously that's not doesn't bring us the benefits of cloud computing. Instead, we do need a mechanism that will adapt to the, say, packet by packet, message by message load variations of the individual application instances and their tasks, and does that with no software overhead. So to summarize the benefits of what we call the dynamic parallel execution environments, the many core arrays with hardware operating systems and the multi-stage arrangements and load balanced clusters of those, and we get the best possible performance for a given amount of resources with maximized utilization. Also, there is essentially a free side benefit from doing the resource management at the hardware level. We don't push up any kind of inter-application security. It's just to be addressed at the upper layer of the software stack. The hardware simply does not provide the mechanisms that could theoretically be exploited by malicious software. Adding this together, and with the PaaS approach, which has a development environment integrated with the execution environment, the users get performance, cost efficient security with high productivity in terms of the application development as well as the deployment and runtime management. And yes, this does not exist in terms of the the execution environment. The code does exist simulated. The processor cores are to be obtained. It would be preferable that the processor core itself would be open source, but it could be a licensed one as well. But the main work yet to be done is the development environment, and we are looking for collaborators. And the point is that this should be customizable for various type of user application fields, like through domain-specific languages and so forth. That the user would have a way to make this development environment do exactly what they need out of it, but the lower level aspects, those are automated by the execution environment. And the interface between the development environment and the execution environment is an open standard. So the development environment, besides being open sourced in terms of the software, also allows the application to be run anywhere. The Throughputer does provide a commercial hosting as an option. And we've actually covered many of these topics already in the other presentations of this conference. We do have a fairly cross-industry major challenge. The entire computation model needs to evolve, address the need to gain performance, not through linear speed up of say, raising clock rates. That's no longer feasible. We need to find concurrency, and we need to also run those dynamically parallelized programs efficiently on dynamically shared infrastructure, and to deal with the overhead that would otherwise become a performance scalability limiting factor. And Throughputer, the dynamic parallel execution environment, takes care of that in the hardware of the many-core cloud processors. And this is a way to address the some of the presentations already addressed this matter, that we need to think of cross-layer optimization instead of optimization only of individual components or individual layers. And this takes the open source and cross layer optimization down to the hardware layer. And as mentioned, we are actually actively looking for folks to collaborate in the realization of the parallel program development environment, in particular thinking of applications that will run on the cloud. And this presents this collaboration opportunities, both say academic language design, development, model, tool, environment design, as well as industrial. If somebody has good domain-specific language for application field that needs performance while running the application in the cloud, there are plenty of libraries and so forth. Those could be addressed to domain-specific languages, and this presents a channel partnership opportunity. Somebody can make their distribution essentially of this open source platform and host it as a commercial service to the users of those libraries and development tools for various application fields. As mentioned, the processor core could be open sourced if available, suitable for the needs, or we also could license the processor core to the fabric, and of course this would physically need to be hosted, so there are plenty of that type of a commercial collaboration and partnership opportunities as well. And that was about it for Throughputer. And there will be a more detailed version of this presentation then published online. If you had any questions, let's go ahead. Sure.
Do you have any collaborators at this point?
Unfortunately not. So this has been a real challenge because this requires custom hardware. So we are currently is the Verilog code and the specifications. So there are no immediate benefits. So this needs to be realized. I mean, we can have the development environment is developed in parallel. But in terms of many of these aspects for the development environment are being addressed, but I don't think they're really taking the benefit of they're instead of doing in software many of the aspects that are getting closer to dealing with this like messaging and so forth, whereas I believe they should really belong to the hardware. So the collaboration has been a challenge to actually get beyond just talking, because we don't have anything. We can sponsor, we are a more startup, we can sponsor anything, and there are some vendors that kind of tend to dominate the physical hardware supply. So it's been a challenge, but we are looking for like-minded. This I don't think this problem really is being addressed in a holistic manner. So the users should kind of take ownership of the technology roadmap. I think the US government is kind of realizing this. We can really spend all our resources in improvements of the solutions of the past decades. We're currently spending a lot of the resources on essentially dealing with the symptoms of not having the architecture that was ever designed for, say, running internally parallelized, dynamically parallelized applications on dynamically shared resources. So we kind of dealing that through indirectly with all types of software abstractions, but we don't have the processor bandwidth anymore to accommodate the additional layers of overhead.
Any other questions? Thank you.
All right.